Welcome to Master of Science with host Professor James McCanney. The good professor's career spans 50 years as a university teacher, scientist, and engineer. Each week, he will explore the rapidly changing world of science as many long-held theories are crumbling under the weight of new data. He will cover the fields of geology, archaeology, meteorology, oceanography, space science, astronomy, cosmology, biological evolution, virology, energy, mathematics, and more. So please welcome the host of Master of Science, James McCanney.
And good evening once again, episode 32. We're moving along here in this ongoing television series, and this is going to go on for a long time. We have the word from above, so to speak, that many more people are watching this every week. So tell your friends, tell your relatives, tell even people you don't like they should be watching this show. So tonight I will be covering aerodynamics and comparing what I call God's wings, the wings of birds, to man-made wings, the wings of airplanes. We'll see what the big difference is. And there's quite a bit of difference, actually. I'll be comparing wings of birds to sailboats, and there's many different types of sails out there when you talk about sailboat, going back to the old square riggers, the Polynesian canoe sails, the Marconi rigs that are used, the modern triangle rigs, the gaff rigs that were used back in the 1800s, and where they had top sails to fill in the little triangle at the top. Big schooners where they had massive amounts of sail on these boats. And how could they get that much sail on a sailboat? Well, how does that work? Well, we'll be talking about all of that. First of all, in the news, you cannot look any place without seeing some kind of headline that there's a planetary alignment going on right now. So if you go out in the evening sky, you can look up in I think it's the evening sky, and you can see 5 planets that are visible. So there's people prophesizing that it's the end of the world, and there's famine and war, and the usual list of characters talking about the destruction and the imminent decline of the world or whatever. And let me just tell you something, that first of all, this is a visual alignment. There are no real alignments. And when I talk about alignments in my work, I talk about electrical alignments. Like for this picture up here right above me, I talked about this last week, where there are literally electrical connections going on in outer space between comets, between planets, between moons and planets, etc. And so that's a whole different ballgame. What they're talking about now, in fact, is a visual alignment. So here you have the sun, and we're in our orbit around the sun, and if you look off at a certain time in the evening or at night, I believe it's right after dark, you can see the planets up in the sky, and your local weather channel has probably a video. There's many videos online exactly where to look and at what time, etc. But it is a visual alignment only, because the planets, if you look at the solar system, are not in a line or some kind of alignment or something. Not at all. And when I talk about alignments, for example, I think it was last week I talked about, or maybe 2 weeks ago, I talked about the Jupiter winds. And back in the 1990s, when the military put up a satellite measuring electron currents around Earth, and they just got this big blast of electrons from Jupiter, and they couldn't figure out what was going on. Well, we were caught up in an electrical discharge that involves the sun and Jupiter. And we got tangled up in the middle of that like a big snake in outer space, and they measured it with this satellite. So that is an electrical alignment, which is totally different, and that is not necessarily a perfectly lineal alignment. So in fact, when you look at the position of the planets now, there's not a single one that is in an electrical or lineal or even near lineal alignment with the sun or with any of the other planets. And all of these electrical discharges are relative to the sun. So if we're coming up, I talked about this, that in a couple weeks, March 22nd to 23rd, we will have an inferior conjunction of Venus. That's where Venus comes between us and the sun. And I talked about quite a bit of time on the Venus inferior conjunction flu. Sounds like the name of a rock song. So the Venus inferior conjunction flu is when we pass through the comet tail of Venus, and also we excite Venus because of that electrical connection, and the tail of Venus becomes larger, and we get this influx of nucleotide material. These are very, what you might call poorly formed, rudimentary biological formations of chemicals, chemical structures, and forming with hydrogen, oxygen, nitrogen, and carbon. So the basis of life. And so when it falls into the atmosphere, you ingest it, you breathe it in, and your body doesn't know what to do with it. So that's what the flu is. It's your body trying to get rid of this stuff. Anyway, go back and listen to previous shows. But I just wanted to start off by talking about the planetary alignment, which is big in the news. Also, I want to mention that whenever there are planetary alignments or visual planetary alignments like the current one, there's always somebody who comes out and says, oh, there's going to be earthquakes and damage due to planetary alignments due to gravity. The reality is that we are gravitationless. In other words, we don't sense any gravitational force from any of the other planets, the moons, etc. And what we do detect from our own moon and the sun, because it's so big, is something called tidal forces. And that's a short-range force and only works when things are relatively close, like our moon. So if the moon had oceans, for example, it would have a tremendous tide that would go around based on Earth, its rotation around Earth. And this would point outwards. The oceans would, if the moon had oceans, this tide would point towards Earth on the close side, because the force at the near side of the moon is more than the force of gravity at the center of the moon. And on the far side, the water would fall away, so to speak, because the gravity there is less than the gravity due to Earth at the center of the moon. And so these are tidal forces, and vice versa. We have tides on planet Earth because Earth is spinning every 24 hours underneath the moon. So that gives us this tide, which moves around the Earth at about 1,000 miles an hour at the equator. Absolutely incredible. But what we see is a rising and a falling of the water on the coasts. And it's more prominent in some places, like the Bay of Fundy has a very large tide, whereas other places have much less tide. And that's due to the force of the moon. And then during full and new moon, when the moon is aligned with the sun, we actually have a higher tide, because the sun is its gravitational field is so large. But these are differential forces. They're a third order force. But taking that away, we are gravitationalists with respect to all the other planets. And you might think of it this way. You know, you send an astronaut out into low Earth orbit and they're going around in a circle. Well, why are they gravitationless? Because centrifugal force they're spinning around like you spinning a rock on the end of a rope. There's a centrifugal force that is an outward force. That's what keeps the string tight when you have a rock and you're spinning it on the end of a string. But out in outer space, what happens, just like the strings force on a rock, gravitational force pulls inward, so there's a balance there, which gives you a net zero force. So that's why the astronauts in low Earth orbit are gravitationalists, even though they are subject to two forces, gravity and centrifugal force. So, and we're the same thing. If we are moving amongst the planets, and that was one of the brilliant observations of Einstein, for example, was to understand that we are moving through this curved space on a straight line. So relative to gravitational fields, we're moving in a straight line. And so we're gravitationalists relative to the environment, the gravitational fields of the other planets. Okay, I don't want to spend the whole show talking about this. I want to get right into the discussion of aerodynamics. Now, this is a complicated topic, but here's what, and okay, I can't help but laugh here. Now, I know there's physicists listening to this and engineers and people possibly work in industries. Maybe there's teachers, maybe there's high school teachers out there that teach science or physics. And when it comes to the topic of lift, aerodynamic lift, we talk about an airplane lift or the lift on a sail, on a sailboat, wind coming by and causing lift on a aerodynamic shape like a sail on a sailboat. They always go back to something called the Bernoulli principle. And it is completely false and misused. Now, a number of shows ago, I talked about the Betz limit as used incorrectly in the wind energy industry to describe the amount of energy you can extract from a column of wind, where you have this stupid three-blade wind turbine that doesn't work. The wind blows right through it. 95% of the wind doesn't even touch the blades. I saw one the other day. The wind is blowing like crazy and that thing is just spinning slowly. Oh my goodness. Anyway, don't get me started on that. But anyway, talking about the Betz limit, the issue is that the Betz limit, like the Bernoulli principle, requires a non-compressible fluid. Now, what does that mean? That means water, hydraulic fluids. Most liquids would be classified as non-compressible. There's a slight amount of compression going on there at room temperature and under normal conditions. But most liquids are non-compressible. That means if you put it into a hydraulic system and you put pressure on one side of the hydraulic system, it'll transfer a force to the other side of the hydraulic system without any loss, without any compression, without any change in the volume inside your hydraulic system. And that's how you can get mechanical advantage. That's why you have this little hydraulic jack, and you can very easily jack up your car with this little hydraulic jack. It's like using pulleys or something. There's a mechanical advantage. But it depends on the fact that fluid in your hydraulic press or jack or whatever you're using is non-compressible. So the Betz limit requires, for it to be useful, requires a non-compressible fluid. The Bernoulli principle, which talks about the difference in pressure based on the movement of your fluid, also requires a non-compressible fluid, which is, like I say, water or something like that. But air is not a non-compressible fluid. It is a compressible fluid, a Newtonian fluid. And so a Newtonian fluid is kind of a general name for anything kind of that has free moving, not in a frozen state, so to speak, or not in a solid state, let's put it that way. And so the Bernoulli principle does not apply to aerodynamics. And it's used all the time incorrectly. Okay, and there, I know there's going to be some professors out there screaming because they've been teaching this. They learned it in college, they've repeated it, but it's very simple. What the Bernoulli principle says is that if you have a fluid moving over an aerodynamic shape, like a wing on an airplane, the distance that the air travels over the top of the wing is greater, and therefore the air has to move faster to come back and meet with the other column of air in the laminar flow coming off the underside of the wing. Therefore, the pressure is less on the upper side of the wing, and that causes lift. It doesn't explain the amount of lift we get from aerodynamic shapes. We get a lot more lift than is explained by the Bernoulli principle. And if you take something like a sail, let's look at a sailboat, and you have this thin sheet of material. It's like cloth. It's like as thick as your bed sheet. It's a thin piece of cloth. So the difference in airflow on the inside and the outside is minuscule. And so the Bernoulli principle, if used in that respect, would not allow for any lift at all. It doesn't explain what we see. And the fact is, let me use this example also for the people, the diehards out there, who are going to kick and scream and jump up and down and hit the desk and walk away because they're mad. And this is, by the way, gets back to something called the professor syndrome. It's actually a psychological state, and they've actually discovered enzymes in the human body, primarily because it's so common amongst professors. And I have that category too. I earned my professorship as a young person. And so it can be, it's something you really have to guard against, let me tell you. When something that somebody tells you is contrary to what your firm belief is, this trap door closes in your brain and resists letting that information into your brain. So all of those professors out there, all of those high school teachers, all those college teachers, all of those engineers working in industry that use the Bernoulli principle to explain lift on an aerodynamic shape like a wing, it's wrong. And the reason is, one of the reasons, there's many reasons, but the biggest reason is that air is a compressible fluid. And I'll explain this. For example, that's why you put air in your tires. You don't put water in your tires. You could put water in your tire just as easily as you could put air. You could put hydraulic fluid into your tires just as easily as you could put air. But why do you put air? Because it's a compressible fluid. It's in the strict sense of the word, that's what we call Newtonian fluid. So air, atmosphere, air like you're breathing right now, is a compressible fluid. And that's why we put it in tires, for example, because what happens when you're going down the road, you hit a bump, the rubber in the tire compresses and the air inside compresses. So if you're hitting a lot of bumps, your tire is going to heat up. Why? Because you're compressing that air, compressing the air, compressing the air every time you hit a bump, and it heats up the tire. So on a hot day, you're going down a bumpy road, your tires get hot. It's because of the compression, and the tire changes shape, and the new radial tires actually are run at a little bit low pressure. They're not completely inflated like a balloon. They're at a slightly lower pressure, and that gives you a nice smooth ride. And saves a lot on your shock absorbers and springs, because the tire itself is a shock absorber, because air is a compressible fluid taking up part of that shock. And I gave the example also when I was talking about the Betz limit of a semi-truck or a car going down the road. A semi-truck is the great example because it has that big flat back end of the box in the back. And you're driving down the road in your semi-truck, and the air comes around the cab, and now they have these cabs with all this aerodynamic windage shielding so that the air comes around the cab and goes back. But what happens when the air comes around the back of that big square back of the truck, it can't get back in there completely very quickly, and it leaves a vacuum back there. So that the back of that truck is literally sucking the truck backwards. And you'll find some trucks, they actually put a little bit of a shield there to allow the air to flow back around. But they're not very effective because you still have the vacuum in there. It still creates a vacuum. But The point is that that same principle happens with a wing, and the real cause of lift on a sail or a wing or a bird's wing or an airplane wing is because what happens is that when the wing enters the air, first of all, it compresses the air. Let's imagine that you have a box of air here, imaginary box of air, and it's just sitting there at room temperature, and all of a sudden along comes an airplane at 600 miles an hour, and that's the wing of the airplane is entering your box. The first thing it does is it compresses that air, because air is a compressible medium. And so the air then flows around the wing, and since the wing is kind of canted above and below, the air hits the bottom of the wing and it causes a lot of pressure. So that's a momentum, that's a kinetic energy transfer to the bottom side of the wing. And as the air flows over the top of the wing, what happens? It can't get back down. It's not a laminar flow. It is not, I repeat, it is not, I'll repeat it again, it is not a laminar flow, which would be the case for the Bernoulli principle to work. It is not, excuse me, a laminar flow. What happens is the air cannot get back down to the wing, just like in the back of the semi-trailer. The air cannot get back down, and it leaves a vacuum on top of the wing. And the faster you go, the bigger the vacuum and the more the lift. And so the lift of an aerodynamic shape, as you go faster and faster and faster, that vacuum becomes more and more and more, and it causes turbulence, which gives you a loss of energy. But that's the cause of lift. And so, like I say, if you had a sail, that's a great example. Bird's wing mimics a sail, it's like on a sailboat, very closely, because the bird's wing is not flat like a airplane wing. A bird's wing is, you have the bone in there in the front part, and you have the feathers wrapped around there, but you have kind of like it's more on the shape of a sail, a cross section of a sail. And so what happens is the air comes up and it hits that, and it gives you an extra boost because the sail or the wing is indented. And then the air comes over the top of the wing and causes that vacuum, and then the air column from the top and the bottom meet again, and you get a little bit of turbulence. But that's when the feathers taper off, and it gives you the minimal amount of turbulence flowing off the backside of the wing. And also take a look here at a soaring wing of a bird. And another thing that happens is the bird wing is at the top of the bird. Most jetliners, for example, have the wings coming off the bottom. There's a few styles of airplane like the Bombardier. Who makes that one? I forget offhand. A company out of Florida. Anyway, the wings come off the top of the airplane. And so that affects how the wind comes as the wind hits the fuselage of the airplane. And it comes around. If you have the wings on the top like a bird, then what happens is that air then is going outwards, and it flows out the bottom side of the wing. And on a bird, on a soaring bird especially, what you have is a kind of a shape like this. So the wind comes out, and it hits the wing as it flows out. Here's the body of the bird. And so it gives you an extra amount of lift because the wind coming around the body of the bird hits the wings, and it slides out along the wings. So the tendency then would be for that air to slip over the side of the wings and cancel the vacuum that's on the top side of the wing. So to prevent that, God's design, God's wing, this is God's invention, not mine, not man's. And man tries to duplicate this, in fact. But anyway, the end of a soaring bird's wings are a group of feathers that point upwards at the end of the wing, and they're flipped up like this kind of. And what happens is that air that's coming off the end of the wing is channeled upwards and backwards. So it cannot get around to the top of the wing to ruin the airfoil, to ruin the vacuum that is built up there because of the shape of the wing. So anyway, then man comes along and says, oh, that's the shape of a wing. And so to build an airplane that is functional, then here is what a cross-section of an airplane wings looks like. And like I said, if you put the wings on the top of the fuselage, that's similar to what the bird goes through. So the air comes off, slides off the wing, and there's some loss there. There's some loss of lift because the air is sliding off the wing. It's not going with the direction. Another thing that's interesting is, like, for example, with the Bombardier, you have the motors on the wing, and that wind coming back from the motor itself, from the propellers, gives you a very high stream of air coming over the wing, so it gives you extra lift. So that's why these planes have these little short wings, and you go, how can the little teeny short wing like that lift up this big airplane? Well, that's because you're going 300-400 miles an hour, and when you're at takeoff, remember, you get in the plane, you go out and you taxi down the runway, and you got to get, say, up to 80, 100 miles an hour, and then you feel that airplane lift. You feel the wings starting to lift, and all of a sudden the nose is up, and off you go, with a lot of power from the engines to get you up to cruising altitude, and then all of a sudden they cut the power back on the engines, even though you're going really fast. One reason is because the air is thinner up there, a little bit thinner. Or if you get up to 30,000 feet or 40,000 feet with some of the long distance airliners today, the air is thinner. But the biggest reason is because now you're going so fast that you have a lot of lift. And one of the biggest things you have to overcome with an airplane is lift and drag. And so if you have very good, efficient wings, then that cuts down on the energy consumption, and you can go longer distances. Okay, so I want to review this, and I want to go back, and I know there's every professor, every person that works in engineering, if someone came up to them and said, explain to me how airplane wings work, they would haul out the Bernoulli principle. They would talk about laminar flow. It doesn't apply. It does not apply, boys and girls, grandmas and grandpas, engineers and third graders. It does not apply because air is a compressible fluid. And in fact, if it were up to the Bernoulli principle, birds wouldn't be able to fly. It's as simple as that. Sailboats wouldn't work. They wouldn't give you lift. And airplane wings wouldn't work that well either. There's the man-made airplane wing cross-section is the biggest difference in distance in an airfoil. But still, if you applied the Bernoulli principle to an airplane wing, it wouldn't work. The other thing, and this is kind of the clincher, the ratio, I don't care what wing you look at, what wing cross-section, the wing or the sail, whatever, the cross-section of the wing is not changing. So the ratio between the laminar flow, the flow on the top of the wing, because assuming Bernoulli's principle, you have to talk about laminar flow on the top of the wing versus the bottom of the wing. It's a constant. It's a ratio. It's a constant, which means if you double the velocity, you're going to get double the lift. If you triple the velocity, you're going to triple the lift because that ratio is the same. And so that's not how lift works. The lift is typically roughly the square of the velocity. The square of the velocity. And so on a Bernoulli, something that if you put a wing in water, for example, you will get a linear, relatively linear graph of lift versus velocity. If you put a wing in air, you get a much bigger lift relative to the velocity. It's squared, not linear. And so that's, I mean, these are facts. These are facts, boys and girls. And so please stop using the Bernoulli principle to try and explain lift on wings. In fact, I saw this was comical. I saw some poor guy he was like I think a high school teacher, and he's doing his YouTube video, and he's doing all of these experiments to show the Bernoulli principle. And then he gets down to lift on a wing, and he goes, and I can see his brain locking up. And he goes, well, air is kind of a compressible fluid. Excuse me, boys and girls, grandmas and grandpas, engineers and third graders. The Bernoulli principle does not work. Now, I can imagine how many graduate record exams, how many senior theses, how many, I can't even imagine the amount of time that people have spent using the Bernoulli the Bernoulli principle to try and explain lift on an aerodynamic wing. It is not applicable because air is a compressible fluid. It's as simple as that. And now let's go back to the airplane wing coming into your box of air. You got a box of air, and all of a sudden, 600 miles an hour, this airplane wing comes into it. You know what happens? It compresses the air. It pushes on the air, it compresses it, and that air has a reaction time to then decompress, and it is much longer than the time it takes that wing to pass through your box of air, which means you have left a vacuum. The air passes by compressed, which means that amount of air is in a smaller space, which leaves you with a vacuum. That's another way of explaining why there is lift on an aerodynamic shape as it passes through the air. So once again, so you have the wing canted, the air comes in, the leading edge of the wing is pretty much circular across a half circle. So the wind splits, it goes equally on the top and on the bottom. And if you look at the actual airflow, the wind actually slides up a little bit before it hits the wing. There's a reason for that. But basically what happens is that the air hitting the underside of the wing is a kinetic energy transfer. Very simple. Less the friction, etc. And so you get a high pressure on the bottom of the wing because the air is hitting it. What happens on the top of the wing is the air comes by, it's compressed. It forms a vacuum because the air can't get down to the wing that fast because the wing is passing through quickly, and creates a vacuum on the upper side of the wing, and that's what causes lift. And that's why it is like the square or even more. And there's a very interesting thing about design of wings. If you get into gliders versus a Piper Cub versus a military jet that's going at Mach 2 versus a commercial jet that's going at 600 miles an hour versus a twin engine plane that's going maybe 400 miles an hour, 300 miles an hour. The wing cross-section design is different. What is the most efficient wing shape for that particular airplane, and the length of the wing, etc. And you'll find something very interesting. I was talking about the feathers at the end of the soaring birds, the condors, the eagles, the buzzards. You look at their wings, and at the end they have those feathers flipped up that divert the wind. And so on a jet airplane, the modern jet airplanes, you will find that also, because the V-wing wings, as the air comes back, it's going to slide down the wing, and it's going to ruin the airflow. Trying to get what you want is the airflow to come over the wings, not slide down the wings. And that's one of the big problems with propellers, is that you have, because they're spinning so fast, you have a lot of the wind that's just flowing off the end of the propeller. And so the end result, that's a great loss of energy, because the wind is coming off the end of the propeller. It's not flowing across the airfoil to give you lift. And that's where you come to, for example, a ducted fan motor. very efficient. And but anyway, on the ends of the wings of a modern jet airliner, you find those tabs that flip up. And the whole point is to ruin that airflow coming down the wings so you don't lose that much efficiency because of the air sliding down the wing instead of going across the wing with the airflow, with the airfoil, I'm sorry. So, okay, anyway, now what I want to do is I want to compare God's wing, the bird, with the various different types of shapes of different wings. Okay, I just want to have a little segue here talking about the professor syndrome, in which I'm sure, like I say, if there's professors of aerodynamics or whatever watching this show, they're all going crazy. And that's what happens, is they cannot handle the truth, especially when it digs into their core beliefs. But I want to give an example. I was at an American Geophysical Union meeting one time, which I used to frequent quite a bit. I don't go to these much anymore because there's a lot of work, there's a lot of travel. I pay for my own expenses, so it's expensive. And I realized that most of the people that go there don't have a clue what's going on, so it's like talking to the wall over there. But anyway, I was at a meeting of and there were some students that came over, graduate students, and there was probably about four or five of them. A couple of young men, a couple of young ladies, and I'm talking about, in fact, this poster was up there, and down below you cannot see from the camera vantage point, but there's a picture, I can show it on the screen here, of a volcano going off, and at night, and electrical discharges coming out of the volcanic plume. These are big, big volcanoes. And what happens is they have these tremendous lightning displays around the shroud of the cinder cone, etc. And these are very high energy explosive volcanoes with plumes going up into the stratosphere. These are enormous volcanoes. And at night you can see this immense activity, lightning activity, and it's going on in the daytime, but it's just more difficult to see because it's in the daytime. So anyway, I'm talking to them about this, and I'm explaining that this lightning is the discharge of the vertical electric field. And standard science would tell you that it's the tumultuous movement in the column of smoke, and it's separating ions and creating a battery internal to the plume of smoke. That it's somehow like a thunderstorm, what they believe a thunderstorm lightning is. And I say, no, well, you can see the lightning is outside of the plume. So if the energy that created the electrical activity was inside the plume, then it would discharge inside the plume itself. That's the point of least resistance. It would not come out of the plume at all. And these graduate students were understanding this. Just then comes their professor, their advisor. And he comes up and he's looking, and he's relatively irritated because his students are talking to me. And that was one of the things they tried to keep the graduate students away from me, because I would poison their minds with the truth. And so anyway, he gets very huffy, and he says, well, this is caused by, the standard explanation. He reels it off. And one of his graduate students, this guy, goes, but the lightning is outside of the plume. And wow, that guy came down on him like an eagle catching a fish in a river. No, he said, and he scolded him. He just put it to him. He said, no, this is due to, and I could tell that the graduate student had to just shut up because he didn't want to offend his advisor. But he knew that I was right, that the electricity that was visible in the volcanic plume was due to something outside of the volcano, not internal to the plume itself. So that's a good example of the professor syndrome. That don't contradict me, I have my mind made up, and certainly don't contradict me with the facts. And of course, there's the great story of Galileo when he goes up to the Leaning Tower of Pisa, and he's teaching his students that the gravity, the a big lead ball will fall at the same rate as a small lead ball. And of course, Aristotelian physics, which they had been teaching at the university locally, said that the bigger ball would fall faster. So Galileo goes up to the Leaning Tower of Pisa. He's got all the students are there watching. They're all standing down below. He drops the big ball and the little ball, the same density, same material, and they fall and they hit the ground at exactly the same time. And the professors that were watching went back and continued teaching the Aristotelian physics that the big ball would hit the ground first because it was bigger. Totally incorrect, but that's a perfect example of the professor syndrome. There are so many things, and by the way, that is one of the big points of this entire series of television shows, is to straighten out all of the ridiculous science that is being pawned off on you, the public. And another great one is that hurricanes are formed from warm water. I've talked about this before. Absolutely absurd. Violates the 3 laws of thermodynamics. It couldn't possibly be true. But anyway, getting back to the Bernoulli principle and the Betz limit, as used in aerodynamics, is completely misused universally in graduate schools. If you go to, like, say you do a Google search, you say lift, what causes lift on a wing? You will find video after video after video on YouTube. You'll find textbooks. You'll find they immediately pull out the Bernoulli principle. It doesn't apply. It does not explain lift on an aerodynamic shape. It simply doesn't. It doesn't apply because air is a compressible fluid, very simply. Okay, so before getting into the comparison of God's wing of a bird with the wings of man, I want to talk about something that's very essential to flight, and that is propulsion. When we have a jet airplane flying, it's got usually 2 or 4 big jet engines. Typically now they're on the wings. They used to be back at the back of the fuselage, which had some advantages, but it had certain disadvantages. So they've locked into this. Even the smaller shuttle jets that go between short hops, etc., are with the 2 engines, 1 on each wing. And the original 747s had the 4 engines, and the bigger planes now, the 777s and the 787s, of course, have the same design with the 2 engines, 1 on each wing, and there's a very, very stable design. So anyway, that is what we call inertial propulsion. If you look at a rocket taking off at if you see a rocket taking off at the Cape, and or any place, if you see a rocket taking off, that is an inertial propulsion system. You're heating up gas, you're heating up something, or a solid booster that would be a solid that's burning, and you have a cone or a conical rear end of the tube where the solid fuel is located, and the hot air comes out the back. So the hot air goes one way, the rocket goes the other way. Newton's law. Equal and opposite reaction and force, etc. So, and the rest is engineering. Those are inertial propulsion systems. You're throwing something out a nozzle in one direction, your device goes the other direction. And now an automobile is a good example of a non-inertial propulsion system. You have an internal combustion engine, it's creating energy, that energy is delivered to the wheel sits on a road, the wheels push against the road, makes the car go down the road. That is a non-inertial propulsion system because you are not throwing something out the back of the automobile to make it go forward. There are jet cars, of course, where they put a jet engine on an automobile and they can go crazy fast. But let's look at, in terms of wings, etc., winged creatures and man-made devices. Okay, so the bird is a very good example of a non-inertial propulsion system. The bird has energy, eats food, creates muscular energy, moves its wings up and down, and as the wing is going through the air, it pushes backwards, and at the same time it creates lift. And in a soaring bird, they're using updrafts. The heat coming off the ground is an updraft, and they're riding that. So as they're falling, so to speak, the air is rising, and so they maintain a given altitude. But once again, they're using energy from the system, their environment. And so once again, it is a non-inertial propulsion system. They're not heating up some kind of gas or fluid and shooting it out the back end. Another form of non-inertial propulsion is a swimmer or a fish. So a swimmer, what? They eat food, they have energy, their muscles are working, and they are pushing against a medium, which is water, and they're using their muscles, and they're not shooting something backwards. A different example would be a squid. A squid takes in water and shoots it out the back end, and that's what causes its motion. And so that is an inertial propulsion system, because he's taking material, shooting it in one direction, and makes the squid move in the other direction. But a whale or a fish or a mermaid or a person, swimmer, is non-inertial. Okay, very important. Whereas an airplane, of course, has a propeller or a jet engine. What does a propeller do? It takes dead air, makes it move very rapidly in the backward direction, and makes the airplane go forward. So it, in a sense, is an inertial propulsion system, because it's throwing water out the back, or air out the back end, or the boat propeller, the same thing, at a high rate of velocity. You're taking dead air and moving it at a high rate of velocity. And the swimmer is different, because the swimmer is taking his arm, and even though his arm is sliding through the water, it's like an ideal swimmer would be one with great big pads on his hands, and so the water is relatively motionless. It'd be like crawling down the hallway on your hands and knees. That's a non-inertial form of propulsion. And the reason I'm going through all of this is because in my younger days, when I realized the electromagnetic nature of outer space, the first thing I did was map out the many different voltages and induced voltages and magnetic fields that result from electrical currents in outer space, and realizing that outer space is full of electric currents and magnetic fields. And what is the cause of these electric fields and electric currents and resulting magnetic fields? And the end result is, I said, well, these are a medium, just like water is for a swimmer. So you can push against these with a properly designed electromagnetic propulsion system. And so I began designing non-inertial electromagnetic propulsion systems. And one of them you can see, it's in my book, Atlantis to Tesla, The Colburn Connection. It was 1981-82 time frame. I was in Los Angeles looking for funding for these, and got involved in the military, the high-level military meetings. I gave talks at things like the 19th International Electric Propulsion Conference in Colorado Springs. Was at the Broadmoor Hotel, but it was a closed military meeting. And then I did a series of talks, and of course looking for venture capital when I was in Los Angeles with the venture capital groups. And that's where I got an eyeful, a real education as to who ran the military industrial complex, and through the venture capital groups that are basically funneling government money into military contracts. And I was one of them. But at any rate, that's a whole nother story. But the point is that the thing I was working on non-inertial propulsion systems for outer space, because what's the biggest problem with inertial propulsion systems? You got to carry all this stuff with you. You got to carry fuel. Fuel becomes a part of the payload. So you have something like a Saturn V rocket, the big lunar launch rockets from the 1960s, 70s, 7 million pounds of thrust, and it takes off like, and as the fuel burns, the rocket becomes lighter, and so your thrust remains the same, so it begins to accelerate. And you're accelerating through the thickest part of the atmosphere. But what if you didn't have to carry all that fuel? The payload is this little teeny capsule up on the top of this thing. The vast majority of your payload and work is to lift the fuel, not the payload. And the same with the space shuttle. You had this huge monstrosity of an aircraft, very heavy, and you're lifting up a payload like a little satellite in the bay doors. So at any rate, inertial rockets are a problem in outer space, and we're not going to get very far with inertial rockets. Like Elon Musk's SpaceX, they're talking about going to Mars. But what do they have to do? The very first thing they have to do is develop a refueling system to get the fuel, because they get up into orbit and they start on the trip to Mars before they can go. They used all this energy, all this fuel to get up to leaving Earth orbit. So what do? They have to take another spaceship, another number of spaceships to refuel the one that is now going to leave for Mars. So carrying fuel is a big, big problem in outer space. And when you start talking about going into outer space to other star systems, you got a real problem. You got to carry all this fuel. And I don't care if you heat it up with nuclear reactors or whatever you're doing, you still got to take a boatload of fuel. And let's compare this to the old sailing days when the Europeans first started. Columbus came across, discovered the New World. You had immediately large groups of people coming in sailing ships, square riggers, and sailing across the ocean using the wind. And those were non-inertial propulsion systems. In other words, they don't carry fuel to throw out the back. They didn't have an engine. They were using the environment to move. And of course, there are things like the solar sail. For example, it picks up on the solar wind and supposedly moves. Then you go back to ion engines, which are another form of inertial propulsion system, where you heat something up, you send it down a track of an electric field, or you could also use magnetic fields for sending material out a nozzle to accelerate it. And the benefit of those is that they can work continuously for long periods of time. So you don't have this huge thrust over a short period of time. You have a very little thrust over a long period of time, but with a similar result. Okay, so the reason I wanted to talk about that is because it's essential to understand flight and the design of the wings in aerodynamic flight. Okay, so the reason I went through that little expose just now about inertial and non-inertial propulsion systems is because in the case of the bird, the wing, the aerodynamic lift part of the bird, the wing, is also used for propulsion, non-inertial propulsion. And that allows them, because of the flexibility and the nature of the wings, it allows them to take off and land without a runway. Far superior to the man's wing, which is fixed and needs a runway to land and take off. And of course, they got around this back in the early days of aviation by having planes that would land on the water. And so these were big, very comfortable airplanes that could fly from, say, California to Hawaii. That was one of the big destinations. And they were low speed, and so they were very fuel efficient, and they could carry a pretty good sized load, passengers and all their stuff, and relatively in comfort. And of course, then you have the dirigibles, the air lighter than air, so a lot of the lift is offset by the fact that you have this big thing full of hydrogen or helium gas. And so all you need is the forward motion once again they went relatively slowly, but they were moving 24/7. So they had flights between Germany, New York City. There's a lot of pictures of the Zeppelins coming into New York City or into South America. They were traveling. The Germans had, and these were luxury liners. You had what, 100 people? I don't know how many passengers. I think it was slightly under 100 people, passengers, in the staff. And they had the best cooks, the best food, and these people would take a number of days. It was like a vacation just going on the ride. And so once again, they would use propellers to move, but great distances, because they offset the lift component with the air and I think the days of dirigibles are coming back. I believe I did a show on that recently in this television series. As I recall, I talked about dirigibles. If not, I'll go back and look at my notes. And if not, I'll do a discussion. Yeah, I'm pretty sure. Yeah, one of the early shows. I don't know which one it was. Okay. But it's important to note that the birds, God's design, the propulsion system is also in the bird itself. And of course, they could land on water, they could land on trees, and land on the ground. Very versatile, versus man's design, which requires a runway to take off and land. Okay. Second of all, I just want to give a little bit of a discussion here of jet engines. And a lot of people don't really know. They see that thing hanging on the wing of an airplane. They don't know much about it. But it's one of the marvels of modern engineering. Absolutely. And it attributed to one of the safest mechanisms for moving groups of people. Put 300 people in this tube and blasted them off on the end of a runway and traveled. What I just saw a flight that was from someplace in the United States. Was it Oregon? To Australia. 17 hours in the air with I think it was a 787. But amazing. But the only moving parts, the only real moving parts, of course, you have valves and you have sensors, you have all kinds of little doors and things in the engine. But the real workings of the engine itself, the only moving part in which you have metal on metal, that's what I mean by a moving part, as opposed to internal combustion engine, where you have pistons moving in cylinders. A jet engine is not like that. The only moving part in a jet engine are ball bearings. Very reliable. That's why they're so reliable. So the burning chamber in a fan jet is very different in a military jet. But in a fan jet, the air comes in, it burns in the burning chamber, and the air is pushing it back out as it expands. It turns rotors, which are then geared to the front of the engine. And then you have these big fan blades that push the air out around the outside of the engine, keeping it cool. And that's where the majority of the thrust comes, is from the fans. That's why they're called fan jets. And they don't use that term too much anymore. When they first came in and first started perfecting these when I was younger, and the fans got bigger and bigger to the point where now it's, I think, about a 10-to-1 ratio of the air coming out the engine is from the fan blades, not the burning itself. And so, but the only moving parts are bearings. It's very, very reliable. And so just a little bit of commentary on that. And let's see. I want to give another example. And this is going to run into next week, by the way. There's no way I'm going to finish all of this next week. I'll be talking about the bird and compare the bird wing to airplane wings, sails, the various different types of sail. Like the Polynesian sail is very interesting. It's inverted. The big part of the sail is toward the top. And the reason for that is because if you're out on the ocean on this twin canoe and a big wind comes up, as your boat leans over and heels over due to the wind, the air spills out of the sail. It's a natural way of keeping the boat upright. But I can see I'm running out of time here. I got about a few seconds left, so just want to encourage you to tell your friends about this show. And that's going to be a great benefit to more and more people understanding the horrifically bad science that is out there permeating universities, the newspapers, the science news media, etc. And to correct that. It's very important to correct that. So we'll talk to you next week.
This has been Master of Science with host James McCanney. Join us each week as James will delve into historical figures such as Nikola Tesla, Albert Einstein, and the great mathematicians as we explore the history of man, Earth, and our universe as you've never seen it before. Tuesdays, 7 p.m. Eastern, right here on the Bold Brave TV network, powered by B2 Studios.